In this lesson, we are solving some problems involving rational functions. Of course, with calculus, which means we are going to be finding the derivative using our quotient rule because of these rational functions. Our first example is the concentration C at T in milligrams of per cubic centimeter of a certain medicine in a patient's bloodstream is given by the function. T is the number of hours after the medicine is taken. Determine the maximum and minimum concentrations between the first and the 6th hours after the medicine is taken. So we have a closed interval here because we're limiting our domain to be between 1 and 6. All right, so we're finding the maximum and the minimum within that interval. So if I want the max and min values, I know I need to find my critical numbers, and my critical numbers occur where the first derivative is equal to 0. So I need to take the derivative of this function. And to do that, we know that the derivative of the function will be the derivative of the top times the bottom minus the derivative of the bottom times the top, all over the bottom squared. So if I look at the top, 0.1t, the derivative of the top is 0.1 times the bottom. Now I'm going to actually square that binomial. Square the first, double the product, square the last. Okay, the derivative of the top times the bottom minus the derivative of the bottom. So I squared it. It's easier for me to take that derivative there. Times the derivative of the bottom times the top, all over the bottom squared. So that'll become a t plus 3 all to the exponent of 4. If I'm squaring a square, it becomes an exponent of 4. All right, so we're going to expand and simplify that. And then you want to set that derivative equal to 0 and solve for the t value, the critical number. And then we'll go from there. So put the video on pause, simplify that, and let's compare our answers. Okay, so when I took my derivative and expanded it and simplified, I got my factored form right here. Now, I just kept a factor of 0.1. I noticed it was common to both pieces of this, so I common factored that out, so I didn't have to worry about that. For critical numbers, my derivative has to get set equal to 0. Then I multiplied both sides by the denominator and divided both sides by 0.1 to end up with this line right here. And then to get t by itself, I got t being equal to positive or negative 3. But negative 3 doesn't fit our domain, so we really only have to worry about t equaling positive 3. Now, because we want the max and the min on that fixed interval, what I'm going to do next, let me just draw a little line across here so that we can separate this into two pieces here. I'm going to actually evaluate the concentration at 1 hour, get its value. So I'm going to sub 1 into the original equation. So I have 0.1 times 1 divided by 1 plus 3 all squared. I'm going to get its value, and then I'm going to evaluate the concentration at 6 hours, and then also the concentration at the critical number, which is 3. Okay, so it's just the concentration, it's not the derivative of the concentration. I want to know what the exact concentration is at those values, and then I'll compare. The biggest one will be the maximum concentration. The littlest one would be your minimum concentration. Okay, and so I have my answers here, but I just noticed I have a mistake in the one answer, which I need to fix up. This is having one too many zeros there. So my maximum happens, maximum concentration will happen at 3 seconds, or at 3 hours, and my minimum concentration is at the 1 hour mark. So I'll just put a therefore statement in here to conclude that. And there we have our therefore statement. Moving on to the next example. The position function of an object that moves in a straight line is given here, and it's good for 0 to 2 seconds. I did not put that the units on this question. I should have. Let's go with our distance is in meters and our time is in seconds. Calculate the maximum velocity of the object over the given time interval. So we're going again with meters. Position is going to be in meters, and our time is going to be in seconds. Okay, so From there, we are trying to calculate the maximum velocity. So we want to maximize our velocity. That means we need the velocity function, which means we need the derivative of the position function. That's the one that we then want to maximize. So once we get the velocity function, it's that one that we need to take the derivative of and set it equal to 0 and solve for the time at which that velocity will give us our maximum or possibly a minimum. We will have to check that one. So try that question, put the video on pause, try it out, and then you can check your work. So when I found my derivative, I found that s prime at t was equal to 2 plus 16t divided by t squared plus 1 all squared. So this is the thing that I want to maximize or minimize. I want to find the derivative of this and set it equal to 0. I really want to find the derivative of that velocity function. So that means I need to find its derivative, or the second derivative. Okay, so take the second derivative of this, and then we're going to solve for the critical numbers of it. So again, put the video on pause if you want to try it on your own, and then you can check your work. All right, so I took the derivative of the derivative and wrote it in its factored form, which I then decided when I went to find my critical numbers, I'm going to actually pull the negative out of the trinomial that is there, so I have a positive leading coefficient in that trinomial, and I just realized I need to tidy up a mistake here. That should be a 4 here, and then the other one should be a square. I'm going to treat it like a quadratic. Yeah, that should be a 4 and that should be a 2. I'm going to treat it like a quadratic and find two numbers that are going to add to 2 and multiply to -3, which should be +3 and -1. So this will factor. Now before I do that, I will multiply both sides by the denominator here, and then I'm going to divide both sides by -16. And when I do that, let me just pull this up here. When I do that, that's going to give me 0 equals the 3t to the 4, and then plus 2t squared and a -1. So from there, I'm going to factor that as a tricky trinomial and then find my critical numbers. All right, so I have solved for t. I got t squared equals -1, which has no solution, but then I got t equaling plus or minus the square root of 1/3, or plus or minus 1 over root 3, or plus or minus root 3 over 3, depending on how you want to write that. The negative time doesn't make sense. We're only looking for time between 0 and 2 seconds, so our critical number is t being equal to the 1 over root 3, which is approximately equal to 0.577, according to my previous calculations. 577. So now I want to double check to make sure that is a maximum at that point and not a minimum. So I'll set up my interval table. I'm going to go from 0 is less than t is less than the 0.577, and then t being between 0.577 and 2. I'm going to make it sure that I stop at that 2 value because that was our set interval here. And we're just going to show less than 2. We're just going to show that that is an actual maximum that happens there. And I want to check the sign of my derivative. Now remember, it was the velocity function that I was working with, and then I had to take the derivative of it. So I need the sign of that second derivative. I can list all my factors here of my second derivative. I had a -16, and then we had a t squared plus 1, numerator, broke down to t squared plus 1, and it also had a 3t squared minus 1. And then the denominator was the t squared plus 1, all to the exponent of 4. So those things collectively, slide this up a little bit, those things collectively make the derivative of my velocity function. And then that will give me a chance to see what the actual sign, or what the behavior of my velocity function is at that spot. So you can pick values and check them there. I picked 0.5 for the first one, and then I picked 1 for my second one. So 0.5 is what I chose here. and I chose 1 here, and then I stuck my values in. Negative 16 is negative 16 no matter what. Anytime I take something to the exponent of 4, no matter what, that's going to be a positive. It's really just the 2 middle ones that I have to be concerned about. I believe this was negative here, and then this was a positive and a negative when you sub those things in. So overall, my first derivative of my velocity, which is the acceleration function, was negative in that first interval, and then it's positive. Shoot, I made a mistake here. Where did I make my mistake? In just copying things down, that's where. Okay, that was supposed to be positive there, and then I think this was supposed to be positive here. I did them in a different order on the sheet that I was looking at here. I think I'm okay now. So overall, this is positive and this is negative. So we have an increasing for our velocity and then decreasing, which does make it a max at that particular value of time. Okay, and then we just need to conclude that with a final statement. Okay, and one other thing that I did before I did my therefore statement is that I actually calculated the velocity at that time, so I put that in my velocity function, which is that first derivative. So therefore, the maximum velocity is about 7.2 meters per second, and it occurs at about 0.58 seconds.